This is a video on tutorial 3 question 2. Okay, but before I start, I need to make very clear that this equation is okay. This is case 3, right? Okay, just to let you know if you remember. We got a lot of case 3. So this the formula sheet itself that is provided by the formula. I mean the formula is for the however it's provided in the formula sheet itself is the same as the case 3 in your mathematics. Okay, it is E rho T and then A cosine something and plus B sine something. But in this case, they are about the same style. So when you're given a underdamped question, okay, typically you have two methods in solving. Either you can solve in typically you will solve in this method. You solve using this method. Sorry. However, if you are asked to find certain phase angle changes and stuff like that, you use this equation. And take note that this R, I didn't explain how to get this R, is that you take P square plus Q square, you will get R. Okay, so maybe I'll write it. Okay, so is this. If you were to ask me graphically what is P in Q and what is R, dude, I don't know. But yeah, just to let you know when you're calculating things, yeah, maybe in the future if I happen to know, then I'll just post a video. But yeah, with this said, you can see that this can be a solution to any question. I mean, this can be a solution for under them. This can also be a solution for under them. Okay, it all depends on how you want to do it. And without further ado, let's start off with this question. I mean this question, tutorial 3 question 2. I started from 8 o'clock. I mean 8 plus until now. Okay, so nonetheless I will be very shocked. Okay, anyway. So the trace shows the displacement time curve of a spring mounted body. Okay, so similarly now we are talking about also the graph itself, same as the tutorial. If you remember last time talk about this. Now we also talk about the graph. So the purpose of this video is the same, just to let you know and the G's in trying to articulate between your variables. Okay. Similarly, the last one also is to promote good articulation technique. The very first part, tutorial 2 question 1. But now in our case, we also need to familiarize ourselves with viscous friction equation and promote good articulation. Maybe I should write it down. So this is why did I close it? Damn. Okay. Hold on a while. No need lah. No need to hold on. I just okay. So in this case, my approach is that okay, I haven't talked finish yet. Okay, sorry, I waste a lot of time. You have a mass of 4,000 kg. Okay, the mass itself is 4,000, and it's released from the space position. This is the initial condition. Okay, at t equals to 0. So you're asked to find all this stuff. Okay, natural frequency, spring stiffness, and all these things. Okay, so if you're doing with all this approach, one thing is to previously maybe hold on. So like last time, we actually define all given parameters first, and then we write down all the equations that is related to what the question asks. Okay, so we have to first define all given parameter. We are given that mass is equals to 4,000 kg. Yeah, mass is 4,000 kg, and then initial condition is 0 velocity at t equals to 0. So I've also stated that the velocity at time 0 is equals to 0 meter per second, and then amplitude itself is equals to 40 millimeter. Okay, so you have to also can check it out. What am I opening here? This is 40 millimeter. Okay. Another thing maybe you would like to get a thing is that what is the time per cycle? Okay, so one cycle is actually 3 seconds. This is 2.5, this is 1, this is 4, and then 3 should be here. So we know that one cycle is about approximately 3 seconds. So we can also write down that one cycle is equals to 3 seconds. And then yeah, with this, and then the question also asks that dude, you're gonna find unknown natural frequency, spring stiffness, the critical and actual damping coefficient. You realize what is critical and actual damping coefficient. Okay, critical coefficient. Okay, the damping coefficient is actually C, while the critical one is C naught. Okay, so where am I? Okay, so if you were to remember last time, we actually say that the damping coefficient, I mean damping factor is equals to C over C naught. It was like vaguely announced, but maybe let's explicitly announce over here is this. Okay, so C over C naught. In your book itself, it's also got tell you. Okay, if you were to go back to here, this is the thing. This is the critical damping coefficient, so you have to really take note of it. And then with this, we'll set up the equation. This is natural frequency, and this is the another form. And then this is the WD. If you go and check it out, this is the equation over here. We have this equation. So far, you already understand this part of the formula sheet. And you got like this thing and this thing and this thing, like wow. Okay, this one is division, but yeah, we got a lot of stuff to actually check it out. So let's go back here, and then with this set, and then the damping factor thing. So with this set, let's start off with our findings. What do we know? We know that mass is 4000 kg, and then what do we know? We know that the period itself. What is the period? Period itself, one cycle is 3 seconds, so we can straight away know our k. We can straight away find our k. So therefore, let me write down. Okay, luckily I didn't continue because this method is wrong. Okay, before we start, okay, I okay by far these steps are correct. Okay, up until here, and then now we need to actually observe how the graph would move. In this case, the graph is actually under them. So for under them, as I mentioned earlier, we have to use our equation from the formula sheet. This is the equation. This is case 3. Alternatively, there is another equation. You remember the alpha thing, but now in this case we use this. Okay, we use this equation, and therefore because why I didn't do is because just now that method. Why I erase away this? Why I did erase this portion is because if you solve for this, uh, you can although you can know, because you don't know C, you don't know WD, you don't know, there is certain things that you cannot solve. So therefore you need to really um find you need to introduce this equation in order to find your variables. And therefore let me write it down. Okay, I've written down a lot of things. So let's start. So observe trend of graph. Okay, so we have to first observe our trend of graph. In this case, you know that only under them has oscillation. Okay, if under them, if you can see, if you remember last time, the graph itself, only the under them has oscillation. The rest are either just nice, there's no damping, or over them. Okay, so with this set, we actually know that this is under them, and therefore we can also use this formula. If you remember, the formula sheet itself has this formula. Okay, x equals to, this is the case 3 formula, uh, having the trend, but it's totally not the same as the case 3, I would say. But the case 3, what I mean is the math case 3. Okay, this okay, anyway, so this equation is what we derived earlier. Okay, and then now let's use this equation. If you remember that this equation can be used to solve for our solution. Unless we are finding phase angle, then we need to use another equation. And then we use this equation, and where we know that the WD, the damping frequency, is equals to the following. And therefore, as you can see, this is the one. Okay, and yeah, and then introduce initial condition to solve for P and Q. So okay, because we don't know our WD, because we have no idea how to solve for WD also, because after you solve for this just now, as you can see, we are nowhere to solving the rest of the equation. I mean the rest of the variables. So therefore, the only method is to solve using um, the condition, the general equation that describes the x. Okay, this equation itself describes the displacement x. Okay, so this describes the displacement x, and therefore whatever thing that describes the displacement x can be described using this equation. And this is why this is a very powerful equation. And then we introduce you the initial, so therefore we need P and Q. So to know P and Q, then we can start to solve what is WD and WN. Okay, actually WD I already know. Later I'll just, in the next video I'll tell you what is WD. It's a little, yeah, but okay, it's a conceptual idea. So to solve for Q, we actually need to sub in our boundary condition. We know that this equation, okay, this equation, the one that we pick up from the formula sheet itself, describes the displacement x. Okay, so therefore our displacement x, as you can see at this position when time is equals to 0, okay, is 40, and therefore 40 is equals to this equation, okay, where time is equals to 0. So therefore when I sub in by 0, you eventually get this one will become 1, so it become P only lah. Then this one will become E naught, I mean E0 straight. Yeah, because T to everything is 0 over here. And then this one becomes 0, sine 0 equals to 0. And you will get P equals to 40. Then now we need to solve for Q. Okay, so for Q, we need to differentiate. Okay, because you know you need two unknowns. You need two equations to solve for two unknowns, three equations to solve for three unknowns and such. So yeah. So therefore we have this x dot. This x dot is the velocity, and you know from our initial condition that our velocity itself at time 0 is equals to 0 meter per second. And therefore you can also do it. But in this case you have to first make a differentiation of this dude over here. You differentiate this, you get the velocity equation. So this is the velocity equation, which is pretty long. Yeah. So this is it, and it's a product rule. So apparently I differentiate this part first. Okay. So this minus omega will come down over here, and then this multiply by this, and then this will keep the same, plus I keep this, I didn't differentiate this anymore, I keep this, and then I differentiate the inner one, so therefore the WD will be multiplied outside. So because it's a cosine to sine, so it's a minus, so minus WD P sine WT, and then and so on and so forth. You will realize that WD are the common term, therefore we factorize out the WD. Now we have to sub in our initial condition. Okay, so initial condition, we know that our initial condition says that x velocity at time 0 is equals to 0 meter per second, and therefore when you sub it in over here is 0. And we also know that P is equals to 40, so we can also sub in our P. And therefore when you sub in to this equation, let's compare. Okay, so where am I? So this portion stays the same, okay, because there is no other stuff. However, when time is 0, this whole thing becomes 0, so it's E0. And then P is 40, cosine 0 is 1, so that's all for 40 times 1 plus 0, and then so on and so forth. And then you rearrange, you get Q is equals to this thing. Take note that this is Wn and this is Wd. Okay, damping frequency and natural frequency. They are both inside the equation itself. Okay, they are both inside the equation. Wd, okay, and Wn. Take note Okay, this is a very important one. And then once you rearrange your sub n WD, you get this equation. You cancel out the Wn. Okay, you get Q is equals to this equation. Now you sub in P and Q, where P is 40 and Q is this equation, and then we just sub back into our equation, our formula sheet equation, which is this dude over here. Okay, and then you'll get this equation over here. This equation is when you sub in your P and Q, and now this is the equation where we can then find what is our WD and so on and so forth. So next video will derive the unknowns. So hopefully it will take about one video, and then I'll do a summary of everything, and then I'll call it a day. See you.